Hello, in this video we're going to perform a von Neumann stability analysis to see why the upper bound of the variable r is less than 0.5. And so a little context, in a previous video we coded with explicit differencing to simulate the thermal profile of a bar, and we noticed that when the r value, which is defined as alpha, the thermal diffusivity, times the change in time, so the time increment, divided by the change in position, so the position increment squared, is greater than 0.5, what happens is the thermal profile of the bar gets really unstable. And so that's why we're performing a stability analysis. And so in this previous video, what we did was we drew out the diagram based on the information that we were given, and then we discretized the time increments with the counter n, and we discretized the position increments with the counter j, and we use the heat diffusion equation to approximate the second derivative of temperature with respect to position, and then to approximate the derivative of temperature with respect to time. And we use this information to derive this equation of the temperature at position j at the next time. And so that gives us the constant R that we mentioned earlier, times the temperature at the next position at the time n, plus 1 minus 2 times that, a constant R at the temperature at the current position at that time, and then plus the constant R times the temperature at the previous position at that same time, and then we use all this information to find the temperature at the next time. And so we're going to use that information to perform the stability analysis in just a moment. First, we're going to start with defining the temperature. So temperature can be defined as e to the ikx times e to the negative alpha k squared t. And so using the discretized counters that we did in the previous video, this could equate to the temperature is equal to E times I times K times the position increments delta X times J, because that's the counter that we used, and then times E to the negative alpha times K squared times the time increment delta T times the counter N. And so if we were to use this information and we were to reapproximate the second derivative of temperature with respect to position and the first derivative of temperature with respect to time, what we could find is that the temperature is actually a summation of some constant A for the material is equal to E times IKX times E to the negative alpha K squared times time, beginning at 0 and going to the material. And so basically the summation is because for whatever K value, if A is the constant, then the K value can also be constant, and that's why it's actually a summation of values. And so basically how we come to this conclusion is by plugging this information in for the approximation of the derivatives. But what we're actually going to be using really is mainly just the information that the temperature is defined as e to the I k delta xj times e to the negative alpha k squared delta tn. And so what we can do is plug this in for the equation that we derived earlier. So if we were to just start at the temperature for j at the time n, we would plug in j for up here, so we would get the same e to the I k delta x j e to the negative alpha k squared delta t n. And then so that's this middle term here, and then we also have tj plus 1 at the time n, so tj plus 1 at the time n. So this is the next position increment over, and so what this would change is that it would be e to the k delta x still, but instead of at position j, we are at position j plus 1. And then since the time is still at time n, nothing really changes. We have negative alpha k squared delta t n. And then similarly, that's the first term. We have the last term here, which is tj minus 1. And so we have the temperature at position j minus 1 at the same time n is equal to e to the negative k delta x at j minus 1 this time, instead of at j or instead of j plus 1. And then because the time is still at the same time, nothing changes with this second e, so we still have e to the negative alpha k squared delta t n. And so if we're looking at the differences between these three definitions here, we can see that the main difference is this has an extra e to the I k delta x because of that plus 1, and then this has one less, so it actually has a negative of the e to the I k delta x, and this should actually be an I, not a negative sign. And so if we were to rewrite this, this would just be the same thing as tj n times e to the I k delta x, and then this would be the same as tj n e to the negative I k delta x. And so we are distributing out, basically, if we were to distribute the exponents of these e's and then factor out the constants or the similarities, that's what we would be left with. And so if we plug this information here into this equation that we derived in the previous video using the heat diffusion equation, we would have the temperature at position j for the next time n plus 1 is equal to, we have the similarities between all three of these is tj n, and so we're just going to distribute that out first to start with. And then so what we have here is, the first one is r tj plus 1n, so we already distribute at the tjn, so we have r, and then what's in the tj plus 1 is the e to the I k delta x, and then plus we have 1 minus 2r tjn. We already distribute at the tjn, so we're left with 1 minus 2r plus, and then we have r tj minus 1n, and so we have that r value. We already distribute at the tjn, so we're left with e to the negative I k delta x. And then so what we can do before we move on to simplify is use Euler's formula, which can be defined as e to the x plus e to the negative x is equal to 2 cosine x. And so using that information, what we have is the temperature at position j at the next time is equal to the temperature at position j at the current time, and then we have the Euler's formula, so we combine these two values here, and so we'll have 2, and then we have that r that gets distributed out, so 2r, and then we have cosine, and then the x value is just going to be what's in the exponent of these e's, and so that's going to be I k delta x. And then we have the plus 1 minus 2r. And since these are all subtractions, we can just get rid of these parentheses. And then what we can do is we can move the plus 1 out to the front. So we have tjn 1, and then we can distribute out the two r's. So we'll have 2r, and then cosine of the ik delta x, and then this 2r is distributed out, so we're left with minus 1. And then so what we're looking for is for this value here within the brackets, we want the absolute value of this to be less than 0. And so basically what we're looking is that it is greater than or equal to -1, so just rewriting this term here, and then less than or equal to +1. And then so what we can do is we can solve this inequality. So the first thing we can do is get the 1 out of this middle, so we'll subtract 1, so that would give us -2 is less than or equal to 2r cosine ik delta x minus 1 is less than or equal to 1 or 0, because we subtracted 1 within the inequality. And so cosine is always going to be less than 0, and a negative minus a negative is just going to be more negative, and so we don't have to worry about this part of the inequality, because again, cosine of x is going to be less than 0, and then negative minus a negative is going to equal more negative, so it's going to for sure be less than 0. So what we're going to focus on is that -2 is less than or equal to 2r times cosine of ik delta x minus 1. And then so what we can do is we can begin just solving this inequality. So we're going to divide by 2, and what we can actually do is divide by -2. So that's going to give us 1 here, and then it's going to flip the inequality, and then we'll have r cosine ik delta x minus 1 and then we can divide by this term here, and so we'll have 1 divided by cosine ik delta x minus 1 is greater than or equal to r. And so now we have the r isolated, and we have just the inequality for the r determining the upper bound of r. And so if we're looking at the bottom here, we want to find what the greatest number of this cosine is going to be, or the smallest number of what this cosine is going to be, in order to find out what the greatest number r can be. And so because cosine is always going to equal less than 0, if we were to have a negative minus a negative. So when I divided over here and negated it, it switched these two values so that it is negative cosine plus 1 or 1 minus cosine ik delta x. And so what we're looking for is for this value to be as small as possible to figure out what the upper bound of it's going to be. So cosine x is always going to be less than 0, And so if we were to have we're going to base it off of the k value. And so if the cosine of this ik delta x were to equal -1, we would have 1/2 is greater than or equal to r. And if we were to have the cosine of the ik delta x to be less than -1, what's going to happen? So it would be, let's say, -2. We would have 1/3, which would be less than this 1/2. And then if we were to have cosine of 1k delta x be greater than -1, what's going to happen is it's going to go towards 0, which would go towards infinity, which would cause the instability. And so that's where we get that the upper bound of this constant r is 0.5 or 1/2.